Right, so as always, pause the video, have a go at these questions. So these are quite tricky. These could take you 20 minutes, 25 minutes, possibly longer. So give them a really good attempt. I would say the A star sections are part D in question 1 and possibly C and D in question 2. So give them a go. When you're ready, press play and have a look at the solutions. Here we go. So part A, find the total resistance of the network. Now, you probably in the exam will get a diagram, circuit diagram. You may not. You may be asked to draw the diagram. So if you're not given a diagram, then certainly draw one and then you can refer to it, and it makes it a lot more straightforward to visualize what's going on. So we've got a simple parallel circuit. We've got 10 and 20 in the top loop, so we add those two together to make 30. We've got 30 and 60 in the bottom loop, so we add those together to make 90. And then 1 over 30 plus 1 over 90. Find the reciprocal, you should get 22.5. Our check here is always that the total resistance of a parallel circuit should be less than the resistance of a particular loop. So the lowest resistance here is 30, so it's slightly less than that. Sounds good. Total current, I equals V over R, 120 over total. Always show you're working out and laid out clear. This is so important, because if you've made a mistake in part A and then just written down the wrong answer for part B, that's 0 marks. If you write I equals V over R, 120 divided by your wrong answer for part A to get the wrong answer for part B, you should get full marks. Now, it depends on the question, depends on the examiner, but in theory, you don't get penalised twice for the same mistake. So it's so important to show you're working out clearly. Part C, determine the power dissipated in each resistor. So we're getting into a little bit more synoptic here. I mean, this is all part of electricity, but we talked about power dissipation being I squared R. So you could do this as V squared over R. That's another approach, but we've decided to use I squared R here. So the first thing you need to do is to find the current in the top loop and the bottom loop. So we know our rules for voltage in a parallel circuit. So each loop has the same as the supply. So we have a total of 120 divided by 30, which gives me 4 amps. On the bottom we have 120 again divided by 90, which gives me 1.33. Okay, so I can find the current in each loop, and because it's the same through the loop, then the 10 and the 20 both have 4 amps, the 30 and the 60 both have 1.33. So then I can use my formula I squared R to calculate the power. I squared R, so it's 4 squared times by 10 to give me 160. The 20 is the same current, 4 squared times by 20 to give me 320. On the bottom I've got 1.33 squared times by 30, and then 1.33 squared times by 60. So this is a little bit more difficult. I think if you've understood about power and power dissipation, and you know the basic rules for voltage in series and parallel, this shouldn't be too difficult. But there's quite a lot to do to get all these answers. This is probably 4 marks, I would imagine. Part D says explain why the power is different associated with each resistor, even though the current is divided between parallel branches. So any explain, especially to do with electricity, is going to be more difficult. It's going to get the high marks. This is probably 3 marks for this question. So in some ways, we just need to kind of describe through what is actually happening. So the power dissipation in each resistor depends on the current and the resistance. Well, all we're doing here is just explaining or referring to I squared R. And that's another really useful thing to do in an answer, is make reference to a formula. Very, very important. So we can see that, well, because of I squared R, resistance in the same branch will dissipate different amounts of power if the resistances are different. So again, all we're doing here is just kind of, I wouldn't say stating the obvious, but applying the numbers to this formula. So in the top loop, it's the same current all the way through, but the values of R are different. We have 10 and 20, therefore the values of power are going to be different. So all we're doing here is getting enough detail and using the correct terminology, but just talking through what's happening, explaining in words why we have 160 and why we have 320, why they're different. Once you've realized that, we can just see, well, it's just because they have different values of resistance. We could also add, probably for a 3rd mark, because we've got the lower resistance up at the top, then that's going to carry a higher current. Therefore, the greater power dissipation will be associated with the top loop and the top two resistors, because we've got a bigger current. So again, it's just talking through what we found. We found that the current was larger in the top. Therefore, because it's squared, the larger current is going to dominate. Therefore, the top loop and the resistors in the top loop will have the greater power dissipation. So this is difficult because we're just putting into words what we've actually done in part C. Let's have a look at question 2. So again, we haven't been provided with a diagram, but they have explained what's happening. So always useful to draw a diagram, and this is a skill that you need to be able to replicate in the exam. So we've got this diagram here, but it says the load is not connected. So actually in part A, RL is 0 or disconnected. So we just have a very simple series circuit. The total is 4 plus 6 kilo. We can find the current, V divided by R, so 12 divided by 10 kilo, and we get 1.2 10 to the minus 3. So that's probably a couple of marks, should be straightforward. Right, part B is, oh, hang on a second, determine the voltage. I didn't finish it. So therefore V equals I times R. We've got the current multiplied by the voltage, and we get 7.2 volts. Okay, so that should make sense, because we have, if RL is not here, then the larger of the two resistances, the 6,000, should take the larger share of the 12 volts, which it does. Okay, so part B is a little bit more tricky. Now, later on in this topic, we will look at voltage dividers, and there's a particular formula we can use, which we could have used here, but it's not essential, as we will see. I suppose what we need to do is just to work out whatever we can find, really. If I know that RL is 3000, I can find the resistance of the parallel section. So 1 over 6000 plus 1 over 3000, find the reciprocal, we get 2000. Makes sense because it's slightly less than 3000. The parallel section is in series with 4000, so we add the 2000 and the 4000 together to get 6000. I can find the total current, I equals V over R, so 12 divided by 6000 is 2 milli. I can then find the voltage across the 4 kilo, because I know the current and the resistance. So it's the current we've just found multiplied by 4000 is 8 volts. So 8 volts of the 12 is across the 4000. So that means that this section, the parallel section, must have the remaining voltage. So 12 minus 8 is 4, and both of these will have the same voltage. So all those rules we talked about in the first lesson, absolutely essential. You must know those, and then you can apply them. So we've got 4 volts across the entire parallel section. So we're trying to find the voltage across R2, the 6000. So it's going to be 4 volts. Okay, so we're getting quite difficult now. Part C, so for what value of RL would the output voltage drop to half its original value? Okay, so the first thing we need to do is to find what that half is. So 7.2 over 2 is 3.6. And then we know that the total parallel section has got 3.6 volts. So if I subtract that from 12, I will get the voltage across R1, the 4000, which is going to be 8.4. Now I know the currents, I know the voltage and I know the resistance of R1, so I can find the current. I equals V over R, so 8.4 divided by 4000 is 2.1 milli. And then I can find the resistance of the parallel section in total. Because if I just imagine that these two are acting as one resistor, that might help us visualize it. Because I know the voltage across the parallel section is 3.6. And I know that the total current through that parallel section is 2.1 milli. So V over I can find 1714, the total resistance of the parallel section. And then I know the resistance of a parallel section is 1 over R1 plus 1 over R2 is equal to 1 over RT. So 1 over 6000 plus 1 over the unknown RL is equal to 1 over the total, 1714. So I can rearrange this to make RL the subject. So take 1 over 6000 to the other side, subtract it, and then we want to find RL, so it's going to be 1 over 1704 minus 1 over 6000. Invert your answer. Is going to be 2380. Right, so part D, discuss the impact of varying RL on the overall current drawn from the battery. and how this affects the voltage output. So similarly to the last part of question 1, we just need to put into words what we've found. And I think this is just, I suppose, clarifying or demonstrating that we've understood what we've done. So rather than just sticking numbers into a formula and getting an answer, we've actually thought it through and we can understand the overall picture. So the first thing is, as we've seen, decreasing RL decreases the resistance of the parallel section. And because that's in series with R1, the total resistance goes down. And we know that I equals V over R, so the total voltage hasn't changed. But if I decrease the total resistance, then the total current will increase. So we've answered the first part. What will happen? We've increased the current. We could also say, well, what's going on with the output voltage? So the resistance of the parallel section reduces, we've said that already, but relative to the 4000, that hasn't changed. So the parallel section, the total resistance has gone down relative to the 4000. So it's going to take a smaller share of the total voltage. Okay, so again, exam tips, similarly to part 1, show your working out, make it really, really clear. For the written longer response questions, be very careful with the language you use. Make sure you get sufficient detail. That will be dictated by the number of marks. So part D might have been 2, 3, 4 marks, depending on the question. So if it's 4 marks, plenty of detail.